may have noticed we have an Italian session. So not by design, actually. Who knows? Maybe it's just the connection of statistics and economics in the Italian system. But we have kind of tried to group them together, and we had some interesting actually submissions, all somehow related with economics or business or something else, and they're grouped together in this particular session this afternoon. To start with Matteo Barigozzi from the London School of Economics, and who will be talking about complex dynamic models in model financial series. Thanks, sir.
Okay. Well, first of all, thank you very much, Ernst and Veronica, for the invitation, and well, also for accepting the paper. And let me just give a quick background of how this paper was born. Can you hear me? Is it working? No, it's not working. And the thing is, I was working with Marc Allen, who is my co-author from Brussels, on analyzing volatilities of financial volatilities, okay? And he's one of the main authors in dynamic factor models in time series. He made a lot of work, and so we were using those methods, which are methods where you basically want to isolate the main forces driving the dynamics of your data set. And while doing that, we realized that after removing those main features, which we call the market factors, still a lot of dependencies were there. And then probably was interesting to analyze those dependencies and see what kind of information we could extract from there. And thinking about that, we ended up finding and knowing a whole literature now emerging in financial econometrics using network methods to analyze dependencies among time series with the goal of stating which are, for example, the stocks in a market which are more exposed to extreme events, which is what happened during the last financial crisis. Some big companies had very big problems, and these shocks propagated throughout all the economy, not only the financial market, through the whole economy. Now, we don't want to go so far here, so this is a starting point of this paper. So this is a summary of what we do in this paper, a very quick and brief summary. And what we do here is studying the network built using volatilities of stocks, of returns of stocks quoted on the S&P Standard & Poor's 100 stock exchange in New York. This is done for the using data for the last 13 years, and we will put a particular focus on the years corresponding to the financial crisis, so 2007 and 2008. Now, the first big question to answer is, okay, we have many time series. They don't have a network structure in themselves. There is no a natural notion of network for them, okay? So how do we define a network for financial time series? And here there are many possible choices, okay? So I don't want to discuss now all the possible choices that have been proposed or that might be possible. We just take a stand and we say we consider something which is called long-run variance decomposition networks. I will give a precise definition of this a bit later on. Just the motivation is this is the most natural thing to do for some econometrician. Now here I have to apologize again. I'm more from the econometrics literature. Maybe you are more from with a statistical background. Not even sure what econometrics is, honestly, but there might be some problems of language. So if I say something that sounds completely unknown to you, just interrupt me and I'll try to explain it, okay? And well, the other challenge is that we will be working with a quite large dimensional system of time series. To be more precise, we're going to have 90 time series observed over a period of about 3,000 years. And this requires the use of some techniques for dimension reduction to analyze this panel. And what we will be using are factor models, which I will explain a bit later, and lasso type regressions, penalized regressions, about which I will not say much because I know this is known to, I hope, all of you. We've seen already some of these applications in the previous talks. And the other thing we are going to do here is, well, our focus will be on some particular quantities which we call financial shocks, and this is again a typical approach in econometrics. In econometrics, the typical approach for studying time series is I have a bunch of observed variables, and I am interested in seeing what an unexpected shock, which is usually modeled as a white noise, an IID process, which kind of effect this shock will have on all the other time series. If you want, is a sort of a counterfactual experiment that people are doing. And this is something that is done a lot in economic policy studies. Okay, I don't say it's the only thing that is done, but it's very common there. And so we're doing something similar here. We are going to identify these shocks and see what happens to the system if I shock one node, one series. Our series will be the nodes of the network. What happens if I shock one node, which is sort of like mimicking the spreading of a crisis, of an event that hits one firm, how does it spread to all the others? I'm giving a dynamic flavor, although the dynamic is used to build the network, but then there will not be a dynamic going on in the network, okay? So just to clarify. And the bottom line is that if we find high connectedness in this kind of networks of volatilities, that will mean that there is high uncertainty in that period of time. Because the more the shocks, the more that the assets, the volatility of assets co-move and are large, the more there is a lack of confidence in the market. If one tries to plot returns of any stock that is quoted on the financial market in the last 15 years, you will see big spikes in volatilities, both up and down, during crises. When there is panic, everybody's selling, everybody's buying, and the uncertainty increases. Volatility is a measure of uncertainty, so that's the framework in which we are going to work. Okay? So in the next slide, I show you the final result. It's highly stylized. The thing is, these are the kind of networks that we will be deriving. Here I just want to say that these are directed networks, that they are weighted, although you don't see the weights on the arrows, but they are weighted. We have weights to attach on the arrows, and each arrow represents the proportion of variance. So each arrow represents, if I shock this asset, this is Bank of America, this arrow represents the proportion of variance of this other asset explained by a shock on this node. This is the kind of thing that we are going to discuss, to derive, okay? Why do I say they are high stylized? Because they've been made sparse in the last step, but all our framework doesn't assume that these are sparse. There can be pros and cons. We have a discussion with the guest editor and the referees about this, and I want to discuss this a bit more later on. But for graphical purposes, I agree that if this were not sparse, then it would be pointless to show it like that, okay? It will be a full bunch of edges with no idea. So these are the largest edges according to some thresholding approach that we used. And what do we see is, well, if we observe it over the whole period, there are not many errors remaining, but what we see are clusters of the yellow nodes, which are the financial stocks, and the blue nodes, which are the energy stocks. If I focus only on the financial crisis period, we see much more interconnectedness, and the financial stocks still have a predominant role. The size of the ball is the centrality according to eigenvector centrality measures. So, and these were exactly those stocks that were more hit by the financial crisis. Okay? So that's the idea. That's where I want to get. Now, from this point on, I will lead you to this graph, hopefully, without losing too many of you during the talk.
Can you tell us what the color
The color represents different sectors of the economy. So yellow is finance, blue is energy, pink I think is healthcare, red is industrial, and then I lost track. This one is a consumer, is in the consumer sector. The division in sectors is a standard deviation that is provided with the data, so it's not our classification. So just to describe a bit more the data, we have a panel of stock daily returns, and here I must apologize again, I use a different notation. You would use P for N and N for T, but I'm using T for the number of observations for each time series, and this is the number of stocks, N, okay? And they have been downloaded from the Standard & Poor's Index. They are daily, so each point in time represents a trading day. We have 90 assets from 10 different sectors, which are stated here. And as I said, this classification is not ours, it's a standard classification. This is the total number of days that we have in the whole period. Then, of course, if you focus only on 2 years, the number of observation is about 500. Okay, there are 252 observations per year. So if I focus on 2 years, that's the number of observations that we are going to have. So pretty large dimensional setting, but still not an ill-posed situation where T is larger than N. Okay, so T is much larger than N. So some estimation problems are not there here because. And what we do is actually we will not consider returns. So returns is the percentage change of a price of a stock from one day to the other. But we will extract some volatility measures for this because if we are interested in studying crisis and uncertainty in the market, is volatility what you should look at, not returns. Okay, so a bit more about the definition of the network. So now I give an overview of the methods that we are using, trying not to be too technical, and the goals that we need to face to go through this analysis. And then, depending at what time it is, I will see what to say about the technical details. So every panel of time series is known to admit the composition of this kind. What are these two things? So there are some white noise processes which we normalize to have variance 1 and to be orthogonal to each other. That's always possible, which we will call shocks. They are shocks, and they will be attached to an economic meaning, these shocks. Okay? And the fact that they are orthogonal, it means that the shock to series I, so the ith component of E is orthogonal to the jth component of E, so they are really, if the word were Gaussian, they would be independent. Okay? We just look at linear dependencies, so let's assume that everything is Gaussian around here. What is D of L? This is a kind of notation that we're using. It's a polynomial in the lag operator. It means that this D of L applied to E will load E at time t plus E at time t minus 1, E at time t minus 2, E at time t minus 3, and so on, going back in the past. And the standard decomposition says that actually this D has an infinite order in principle, but that's a technicality. So what is important is that D of L, if E is orthogonal, D of L contains the so-called impulse response functions. So it tells us how a shock on series I affects component J of Y. Okay, so this is a squared polynomial matrix, n by n, and each entry has this meaning at each leg. Now I can, from this decomposition, I can build explained variances, sort of how much is the sum of squares of D of L of each row of D of L, for example. And this will define our network. So basically, if I want to define the network, I have to find this matrix out of my data. I observe Y, I need to find D of L. That's the whole purpose of the thing. And what people do usually, while this is not possible to estimate like that, because I don't observe E. E is an unexpected shock. I don't observe it. So people usually invert this process. They assume that this is invertible, and they have a model in which Y depends on its past. That is called vector autoregression. Okay? And given the vector autoregression, then you can estimate that, reinvert it back, and you get that decomposition. That's the idea. The problem is, in a vector autoregression, if I have many series, I have far too many parameters to estimate. Okay? If I had 5 series, I could estimate that with an ordinary least square approach in the simplest way. Maybe not the most efficient, but the simplest way is that. But here I cannot. N is too large. I will have order, if N is order of 100, I have order of 10,000 parameters to estimate. So something has to be done. And typically you find 2 solutions, at least. 2 of the most used solutions in this setting are the following. Are either using factor models, where we say that actually here I need far fewer E than Y's to find this matrix. Okay, there is a sort of singularity. There are fewer common features in my panel that are enough to capture most of the variability in the data. That's what a factor model is in a dynamic setting, but also in a static setting, that's the idea. Okay, you have many variables and you want to summarize the information in many variables with very few indicators. Okay, 1, 2, 3, depending. Okay, here it will be just one. And the other way is, well, I have a linear regression, because VAR is a linear regression of one variable on the past of its own past and all the past of all the others, and I can use some sort of penalized regression approach. Okay, lasso, adaptive lasso, group lasso, elastic net. These are all options that we explored in this work. Okay, and there are a lot of, these are the first papers proposing these approaches, but then they've been extended to time series in other papers. Now the point of our paper is all in the last part of this slide. You can use either one approach or the other approach. Our point is the two approaches should be used one after the other, because they capture two different kind of dependencies that you have in the data. So for us they are complementary. They are not one the substitute of the other. That's the idea. Because what are these common factors that you can derive? These common factors in the financial literature describes them as market, non-diversifiable effects of the market on the panel. Basically saying that, well, if you have many series, their variance is all determined by the variance of the latent factors that drive them. It's a sort of law of large numbers, if you want. That's a convergence in mean square. That's a sort of law of large numbers. It's saying everything that is left out is noise that has a variance that goes down as the number of series increases, disappears. The contribution disappears. So this is a cross-sectional law of large numbers. Take an aggregate, take an average of your data, and when you take an average of your data, you're wiping out everything that is not a common factor. However, in more recent papers, listed here, it has been shown that what is left out might still have a lot of cross-sectional dependence left in. Okay, so the law of large numbers in the simplest case assume that the residuals are IID. Here, what if they are not independent? What if there is some dependence left? Well, if it is not too much, you can always decompose the two things, but then how much is this residual dependence? And again, the law of large number will kick in at a certain point. It must. Okay, but it might kick in with a slower rate, much slower rate, saying the residual dependence are important even if you have many variables. So for a financial person, pricing a time series according only to the value of the market, pricing an asset according only to the value of the market, which will be the factor, is not the right thing to do, because that series depends a lot on all other series conditional on the market. So that's the idea. So we need to take this into account. And well, there is a problem in this thing here that I can always put something here in the middle, any invertible matrix and its inverse, and I still get the same representation. So there is an identification issue that we will have to challenge. Okay, so that's the whole idea of what we're doing. Now, very few words about factor models, because there is not much time. The idea is, let's go straight from here. The idea is, I have my panel of time series. I can decompose it into two parts. There will be a part written like that, where these are n time series. These u are q of them, where q is much smaller than n, and is the so-called market shocks. This U is a white noise. So again, this is the kind of representation. We have a shock hitting the Y through its present and its past. So this matrix of legs. And we call them global shocks or market shocks. And they hit like that. And these U are few, but they are common to all series. They are pervasive. Okay, this is the market, and this is their effect. And this is what left out, which is called idiosyncratic component in the language of factor models. And the idiosyncratic component still has cross-sectional and autocorrelation, so it still has a lot of dependence in it, although weak in a sense defined by the spectral densities, but the idea is it's weak, but it's there, and it might not be negligible. That's our point, okay? Although in the limit n going to infinity, that's going to be negligible with respect to the other, we're working with a finite n in the end, in practice. So let's try to be real. Let's not to be fooled by asymptotics, okay? Asymptotics is very nice. It's very useful to understand how things go, but then this is exactly our point. So we were working with this kind of series. We were just focusing on this term, and then we realized that here there are a lot of things going on that we didn't account for, and that might be useful to account for them. So that's the model we work with. And so we're going first to take our data, separate it in these two pieces, and then we focus on networks for Z. And the idea is we focus on networks for Z because the U is pervasive. So through the U, everybody is partially correlated with everybody else. Well, it's for sure correlated, but there are intuitions, not proper proofs, that can tell you that roughly that's what's going on. Okay, so if I were looking for a sort of network, any kind of network based on linear dependencies or linear conditional dependencies for this component, I would get something that is quite full, and it's almost impossible to threshold it, because if the links will have more or less the same order of magnitude. That's exactly what the factors are. They are pervasive in this sense. While here it's a totally different story. So we focus on a network for the idiosyncratic components, and so we have two sources of variation. We have the U's, which are market shocks, and then we have the E's, which are the idiosyncratic shocks, which have an effect on all series. I'm not assuming any sparsity here on their effect, okay? I'm not assuming any sparsity. I'm assuming something about the cross-sectional dependence based on eigenvalues. If you want, I'm assuming that the largest eigenvalue of their covariance matrix and their spectral density matrix is bounded for any n, so it's finite, but I'm not assuming sparsity, and not even, of course, that to be diagonal, because otherwise the point would be lost. There would be no dependence left. Okay, so given this D, the network is defined as follows. We have n vertices, which are the n-time series, and this is the edges set, which is based on this weight, which you see they contain the sum of the squared entries of that matrix. That matrix is a polynomial matrix, so it has different legs, and this h is telling us how much in the past we are going. Okay? They decrease as h increases because they have to be summable, and this is what you get. But the question where to stop with h is an empirical question, so in the paper we made different trials. We set h equal 20, and these are the results reported in the paper, with 20 means 2 weeks of trading. Okay? So quite some time. Sorry, 20 means 1 month of trading, not 2 weeks. It's 5 days per week. And we tried also with smaller values, and so this is what we're going to compute. So roadmap is take your data, separate into factors, get the idiosyncratic component. On the idiosyncratic component, extract this D and compute this network. Now there is no sparsity assumption, as I said, throughout this point. I'm not assuming that this is sparse. But now we make an assumption. This is some normalization of the weights, but I'll go back to that later on. We make an assumption that actually the Z can also be written as a vector autoregression, because that's the operative version of that model. As I said, this can be estimated. The other version cannot be estimated. And I assume that this F is sparse, because these Z are many. If this is not sparse, then I have no idea how to estimate it. I still have 15, including questions, so 10 minutes, right? Yes. Yeah, okay. Just to see what to cover and what to skip. Okay, so this is our assumption, and then if this is our assumption, then there are plenty of techniques to estimate sparse vector autoregressions. Okay? So that's not our contribution. Our contribution is separating into common and idiosyncratic, but once you have the idiosyncratic, then there are standard techniques to estimate a sparse VAR. Okay? So the possibilities that we explored in the paper are elastic net, group lasso, and adaptive lasso. And of course, they don't give exactly the same result, but the final message of the paper is more or less unchanged if we use the different methods. Okay, this is just out of curiosity. If I estimate a sparse VAR, attached to it there is another network which is basically the sum, so it is based on the coefficients of this matrix, right? And what is this matrix measuring? This is measuring the conditional dependence of each series on the legs of the others. Okay? Each entry, ij, of this matrix is measuring the conditional dependence of zi on the past of zj, given the past of all the other series. So that's a natural thing that can be plotted as a graph. And indeed, there are works by Dalaus and Eichler that propose this as a graphical version of VAR. It's interesting, but it's not interesting for us in terms of looking at it as a network. For us, the sparse VAR is just a tool to get to the moving average version, because the moving average version is telling us how a shock to a node affects all the other series. And that's the kind of counterfactual experiment we're interested in, to see how the financial crisis affected shocks one after the other, stocks one after the other. So that's that's consistent with the traditional spirit of macroeconomic analysis in time series. Just to say this, so we do have another network in our paper embedded, but we're not actually studying this, okay? We just say that it exists, it can always be defined, but it's not the object of interest for us. I'm not saying that it's not interesting, it's not the object of interest for us, let's say. Okay, so I estimate the VAR, I invert it, and I get my matrix of coefficients from which I compute the network. However, that, as I said, is not identified. I can always put an invertible matrix here, and that matrix must be such that the residuals of the VAR become orthonormal, because that's our assumption. Now, the choice of R is something, I mean, you can estimate it using some statistical assumptions. Again, here it really depends which approach do we take. We're taking an economic-driven motivation in the choice of R. And so one possible choice is take an R such that the covariance of the residuals of the VAR is written like that. So for example, the Cholesky factor would do the job. Okay? However, if I pick this as the Cholesky factor, that depends on the ordering of the V. If I change the ordering of the V, that changes. So it's not a unique choice. So the next question is, how do I order the stocks such that I pick the R that I want? And again, this is a matter of choice. In the original paper by Diebold and Ilmath, which is in the Journal of Econometrics, from which our idea started from, they propose another kind of matrix, okay? And one can think of ordering the shocks, for example, based on the properties of each single stock, other variables that you observe for each single stock. There are plenty of possible choices there. Our choice, since we're speaking about networks, is, well, let's look at the partial correlation among the shocks. The partial correlation is capturing the linear conditional dependence among those VAR innovations, and since they are VAR innovation, is the contemporaneous dependence given all the past dependencies. Okay, I first control for all the past dependencies, then there is some contemporaneous dependence remaining among our component, and then I can look at the precision matrix, which is this C, and the related partial correlation. And then I look at centrality there. Why? And I order the shocks according to the centrality there. Why that? Well, because the most central shock is the one I want to hit first to see what happens to a crisis, okay? I want to hit first the most central, I want to take the most central shock. And start from there and see what happens. That was our motivation. Okay? If you have other suggestions, I'm really happy to listen to them. Okay? So that's the idea. Then how to estimate the factors is something that we skip, and how to compute volatilities from returns is also part of the story that we skip. So we estimate the factors, and then we estimate a sparse VAR in different ways. That's what we do. So let me go to the results. Okay, so this is a summary again of the data. And the shock common to all volatilities account for about 40% of the total variation of volatility. So the market is explaining 40% of the total variation in my panel. What about the remaining 60%? That's exactly the focus of our network analysis, on that remaining part. There are measures on how the market affects each single sector that we reported here, but that's not really the purpose. This is instead about the sparse VAR. So we got a 5-leg VAR. This is one estimated with elastic net. Now elastic net is not just sparse, it has a ridge part, an L2 penalty and an L1 penalty, and it's a combination of the two. Okay? So here in our choice of the balance that was dictated by some information criteria that we used, we got something that is quite towards the ridge. That's the reason why we get a not so sparse VAR. But still, as I said, the VAR for us is a tool, and this is what we get. Now, positive weights are in red, negative weights are in blue, and here I always highlight in this square, these are the energy stocks, these are the financial stocks, and these are the cross dependencies between the two sectors, okay? And the sectors then are other squares on the diagonal. It's interesting how this is capturing everything inside and much less outside the financial thing. When I look at the financial crisis, it's much more full, and I know there are comments about this, but still, this is what we get. And just to compare it with the group Lasso, the group Lasso does a different job. It's much more sparse, as expected. Then I will not show you the result with the group Lasso here. They are in the appendix. Okay, so then I have the VAR innovations. They have a partial correlation network, as I said, which is shown here. They can be ordered according to their centrality, which is what we have here. These are the most central stocks that we use for identification, and the financial companies play the biggest role. And this is the network that we estimate in the end, which is not sparse. Okay, all these entries are different from zeros. Then in red, they are the largest ones, those above the 99th percentile of the distribution. Okay, and just to have an idea of what they do look like, these are the values. These are percentage variances, okay? And they're quite small. They're quite small, but a 2% of variance explained by a shock to one series that is spread to another series is not actually a small number for people working in a stock market, okay? So then we did some thresholding. Here I show you the result of one possible thresholding for the two cases, and this is the heat map version of the graph I showed at the beginning. Okay, and then on these networks in turn we can measure centrality, again like eigenvector centrality, and see which are the most central, but I mean we see it just by looking at it, which are the nodes that have the most important role. Okay, I'm done because I want to leave some space for questions. Thank you.
Any questions?
Yeah.
The lasso, elastic net, this group lasso, are they done in a node-wise fashion? So one node versus all the others, and then you reconstruct the matrix?
Let me think about it. Yes. I think they're done like that. Sorry, now I don't.
The covariance.
Yeah. The other thing I didn't say, the group lasso is fixing the group in such a way that if the coefficient at -5 is not 0, then the -4, -3, -2, -1 are all non-zero. Okay, so if there is an effect at -5, there must be also at -1, which the elastic net is not taking into account. They can be some inconsistencies, if you want. Okay.
Other questions? Have a question? Basically, one thing that is sometimes observed is basically it looks sometimes the additional volatility might disguise itself as additional connections, basically. So probably because the collapse of Gaussianity, maybe, but
that's a possibility. Yes.
So to what extent? So you've already said basically during the crisis, volatility goes up, and so you see a high volatility.
Yeah.
To what extent could the additional links that you kind of infer be the result of just that, and rather than really additional changes to the network? No.
I see your point, and I think they do matter. That it does matter in the. So I mean, this phenomenon, I think it was expected. Let's say, okay. If I think of increased volatility, then I expect more things. So it probably affects the structure of the network. On the other hand, I'm not sure this is bad, because the kind of network we're looking at is an explained variance network. So that's exactly what we want to see, if you want. If I go backwards and I know what I want to see, well, then probably this is what's going to happen. Then I could rescale all the variables, but then I lose the unit of measure, and I don't think this is the point in this kind of study. I mean, there is a relation, of course, and it's a matter of saying this relation is bad because it's hiding something or is giving us a spurious result, as you might think, or instead this is exactly what I would like to see. I mean, if volatility increases, because that's a matter of which is the definition of network that I'm using, right?
You could, for instance, do some bootstrapping, basically, or just where you really do not expect any links whatsoever, and keep the volatility just to check if you would actually infer those links.
Okay, that's a good point. Yes, that I didn't think about. Yes, sure.
Additional questions? Okay. If not, then let's thank Matteo again.
Thank you very much.